Okay, so we will have another example. Okay, so this will be the fifth example in this series. Okay, so please be reminded that this is actually the part 7 or the seventh video in this series, which talks about shear and moment diagrams. Okay, so let us have now this example. Okay, this type of beam. Okay, consider this type of beam. Okay, so you have uh, this type of loading. Okay, it is trapezoidal in shape, and then it has there is an existence of a um, this is a moment. Okay, internal moment located 3 meters from the leftmost support. Then we have ruler support at the left side, and then pin support at the right side. Okay, so without further ado, I will try solving this one. Okay, so we all know that. Okay, so let us say this is A and this is B. Okay, so this let us say this ruler support has a reaction. Let us say AY. And since this is ruler, it has no, it will not experience any resistance um, uh, parallel to the line of motion of this ruler. So it will only have, experience one reaction, which is AY. And for this pin support, it is possible that there is not just only vertical but horizontal. So let us assume, okay, there is two reactions which are Bx and By respectively. Okay, Bx is the reaction at X component and By is the reaction at Y component. Okay. Okay. So first, we're gonna solve for, I will try solving for the reactions in so that we can draw the shear and moment diagrams. Okay. So let us say summation of B is equal to B is equal to 0. Okay. Let us say um, to the counterclockwise as positive. Okay. So let's um, solve. So let us say your B, okay? So since we are summing up moments at B, so um, we take um, B or point B as the fulcrum of this beam, and then everything rotates, okay, relative to B, and everything rotates relative to B. Okay, so let us say this is your steady point or fulcrum, and the rest will rotate. Okay, so relative to B, this AY will rotate clockwise. So therefore your AY is negative AY. And then since it is a vertical reaction, its perpendicular distance relative to B is 4 plus 3.5. Okay? 4 plus 3.5. 4 plus 3.5 is 7.5. Then, we'll try this distributed load. Okay? As you can see, there is distributed load 10 kilonewton meter, and relative to B, this 10 kilonewton meter per meter load will rotate counterclockwise, so it is positive. Okay, so 10 kilonewton per meter plus 10, okay, it is positive. So since it is rotating counterclockwise relative to B, okay, so 10 times the length of 10 kilonewton, which is Okay? So first and foremost, we will divide it in a triangular one and then the rectangular one. Okay? So for rectangular one, okay, for the rectangular portion of this loading, this 10 kilonewton has a length of 3 meters. So we will multiply it by its length. And then we multiply it by its moment arm. Okay? Relative to B. And the moment arm relative to B is 3.5 plus the half the length of your rectangular distributed load. Okay? So because the center of gravity of a rectangle is located L over 2 and the L here is 4. Okay? So we'll have 3.5 plus 4 over 2. And then let's go to the rectangular one. Okay? So since this rectangular portion seems to rotate counterclockwise, so it's again positive. Okay? So the area of your rectangle is 1/2 times B times BH. Your B here is 3.5. Okay? And your H here is obviously 10 kilonewton. And then here, the centroid of your triangle is located L over 3 from this left support. Okay? Okay. L over 3 from here. But somehow, this L, so therefore, it will be 2L over 3 in this portion. Okay? And your L here is 3.5. So therefore, its centroid is 2/3 of 3.5. Okay? And then, okay, is there another loading? Yes, there is a isolated moment, okay, internal moment at the middle, located at 3 meters. So, since it is counterclockwise, so it's positive, so plus 8. And then, all of that, you will equate to 0. So, therefore, we can have the value of your AY. Okay? So, I will just get my calculator. Okay, so we can get the value of AY, okay? You just transferred AY to the left side and then you will, this whole, okay, this whole values, you divide it by 7.5 and you will get AY, okay? So 10 times 3 times 5.5, which plus, okay, 0.5 times 3.5 times 10 times 2/3 of 3.5 and then plus 8 and then divide it by 7.5. So you will get 28.511. Okay? So since we get a positive value, so therefore our assumed direction of reaction AY is correct. So AY is 28.511. Okay? So we have done, okay, summing ups. Okay? So maybe let us check to avoid error in our late solution. Okay, so 28.511 is correct. Then we will have another one, okay? So let us say, okay, so So we have sum up moments equals 0. So we have sum up moments x and y. Okay, so let us start with x. So summation of forces x is equal to 0. Let us say to the left, to the right as positive. So we have negative bx. Okay, because it is going to the left. Okay, so it's negative. So negative bx equals 0. So therefore, bx is equal to 0. Okay. So let us write. Okay. So let us write the values first. So that, okay, this is 0. Okay. Then we have by. So we can get the value of by if we sum up forces vertical is equal to 0. Let us say upward as positive. Okay. So we have values of ay plus by minus, okay, this we concentrate first on this rectangular side. So we have minus 10 times 3, okay, because it's a rectangular load. So 10 kilonewton meters times the length 3, I know 4 meters. 4 meters, okay. So the 3 meters is the distance from your support A to the center of your internal moment. But the length of your 10 kilonewton meter is 4 meters. Okay? Okay, so let us correct this one. So since this is 4 meters, so this should be 4. Okay? Okay, so this should be 4, not 3. Also, okay, that's correct. So let's change the value, okay? So we need to be careful, class. We might not get the correct answer, at the reactions. So therefore, our shear and moment diagrams will be erroneous. Okay. So it should be 35. Okay. 35.844. Okay. So let's check. Okay, correct. 35.844. Okay. So we have 10 times 4. Okay. AY plus BY for summation of forces or vertical is equal to 0. Upward as positive. Minus 10 times 4. Minus 1 half. Okay. The area of this triangle. Times 3.5 times 10 is equal to 0. Okay, so we know that our AY is 35.844, and then BY is equivalent, okay, we don't know, that is what we are looking at. So negative 40, 1 half times 10, 5 minus 17.5 is equal to 0. So we get the value of BY. Okay, so 40 plus 17.5 minus 35.844. Okay, 21.656 kilonewton. Since we get a positive value, so therefore we know that it is upward. Okay, so we all know that if we get a positive value for a reaction, it means that our initial assumed direction is correct. Okay, so BY is 21.656 kilonewton. Okay, so we have the reactions. Okay, so we will go drawing the shear and okay, we will construct the shear and moment equations, okay, so that we can draw its shear and moment diagram. Okay. Okay, so I will erase this one. Okay. So since this is a video, you can rewind any moment in which you want to repeat for some clarifications. You can do it anytime. Okay. Okay. So first of all, okay, since in order that um, we can write the shear and moment equations of of a beam given a certain loading, we need to see to it that it's a distributed loading, for example. Okay, so here we can see a distributed loading, but somehow this rectangular this distributed loading has different shapes, changes its shapes. Okay, so we have 10 kilonewton meter, which is rectangular, and then we have a triangular. It ends up with a triangular loading. Okay, so we need to convert this into its equivalent loading. Okay, so its equivalent loading is like this. Okay, it should be a sum of two. Okay, a sum of two uh, beams like this. Okay, it's not the sum, actually, it's the difference. Okay, so it is equivalent to this loading, distributed loading of 10 kilonewton meter minus this triangular load, which starts from 4 meters and then will continue for the length of 3.5 meters. Okay, so this beam is equivalent to this beam minus this beam. Okay, can you imagine? Okay, so it will be equivalent to this and this. Okay, so why do we do this? Okay, so in order for your shear and moment equations, as we discussed on part 1, is only applicable if that distributed loading, okay, as soon as it starts at any point from the left supports, if that is a uniformly distributed rectangular load, for example, uh, it should continue from that point until the end, until the right support. So if it is not continuous, you should make it continuous, and then you should convert it into sum or difference of two continuous loadings. Okay, so just like this, it starts rectangular but it ends up uh, triangular. So we cannot easily write its shear and moment equation. Okay, so we need to convert it into equivalent loading, in which that loading should be continuous from the beginning. Okay, from where it begins. Okay, so here this beam, this rectangular loading, it starts from A and then ends at B. Here it starts 4 meters from A and then it should be increasing. Okay, so if it is the other way around, if it is decreasing, you need to convert it already into another load. But here it is equivalent to this loading, 10 kilonewton meters rectangular minus 10 kilonewton meter triangular. Okay? This is triangular starting from 4 meters from the left support. Okay? Or from A. So, if that is the case, we can already write the shear and moment equations. But first, we need to divide this. Okay? We need to divide this into sections. Okay? So, let us say that the first section here is here. So, let us say this is your section A. Here. Your section A, or let us say, no, section 1, which starts from A to the center of your um, internal moment. And then your section 2 is at the middle, okay? Here, from this moment loading or internal moment loading until the end of your distributed load. This is section 2. And then after that, the triangle throughout the length of triangular loading, let us say it is section 3. Okay? So then, we now solve this one. Okay? So let us say section 1. X here starts at 0 to x is equal to 2. I know. X is equal to 3 here at the end of section 1. Okay. So therefore, okay, so let us say we start at A. Which has 35.844 kilonewton, and then there is a distributed load, okay, at any value x. Okay, so this is section 1. Since there is no horizontal loading, so we take it as it is. So therefore, your shear is equivalent to 35.844 minus, okay, so this is 10 kilonewton meter. So we have 10x. Okay, since this is a downward force, so it has sign negative 10x. So this is your shear equation from x equals to 0 to x equals to 3. What about your moment? Your moment will be equal to so it will be equal to, moment is equal to, okay, we have 35.844 x minus 10 over 2 x squared. Okay, so please remember from your shear and moment equations, okay, in our first lesson. Okay, so here, as we can see, if it's a distributed load starting A, distance A from your leftmost support, you will use negative W times x minus A. And for moment, negative W times x minus A squared over 2. Here, clearly our A is 0. So therefore, since A is equal to 0, because it starts from the left support, so A is equal to 0. So it will become negative Wx. Here, the W is 10. Okay? 10. So we do this. Okay? So I hope you will get, okay, the application of our first video. Okay? So we have M is equal to 35 0.844 x minus 5x squared. So this is your moment equation for section 1. And then we have section 2. So here, x is equal to 3 to x is equal to 4. So here we have a vertical value of 35.844, okay, vertical point load, and then we have distributed load of 10 kilonewton per meter, okay. So we already finished, okay. The x here starts from the leftmost support until such a time that there will be 8 kilonewton meter, okay. This is the direction, 8 kilonewton meter load, okay. Okay. So therefore, we have V is equal to 35.844 times okay. No? Okay, so since we are already done with section 1, so minus 10 times 3, okay? Minus 10 times 3, since we are already done with section 1. So, all over the length of section 1, up here, 3 meters, okay? So, 10 minus 3, okay? Minus 10, okay, sorry. It should be minus 10 times 3 minus 10 times x minus 3, okay? So since so therefore we have 35.844, okay? So it will become 5.844 minus 10 times x minus 3. So this is your shear equation for section 2, okay? So we continue in this figure. So we have moment, okay, section 2. Continued. So here, your moment, okay? So we have 35.844 x minus, okay, so since it is continuous, we have negative 10 x okay. Okay, so I'm sorry. So it's actually, since there is no change in loading with relative to V, it should be, it's the same. It will be V is equal to 35.844 minus 10x, okay? So there is no change in V. Okay, so there is no change in loading in shear. But somehow in moment, it's different. 35.844 minus 10x squared over 2. Okay, so there is a counterclockwise moment load. Okay, if it is counterclockwise, it will be negative. So if it is clockwise, it is positive. So it will be minus 8. Okay, so we will have M is equal to 35.844 35.844 x minus 5x squared minus 8. So this will be your, okay, we'll make it smaller. Okay, so this will be your formula. Okay, this will be your moment equation for section 2. At x equals to 3 to x equals to 4. Okay. So what about section 3? Is we have section 3 where x starts at 4 and it ends at 4 plus 3.5 is equal to 7.5. Okay. So we have v. So, okay. So let us use this drawing already. Okay. So since we have an upward loading of 35.844, okay, 35.844, that is be your V, okay, 35.844 times X, okay, and then from 0, okay, from 0 to 4, we have a uniform loading of, I know, there's no X, it is just that it will be negative 10x. And then, okay, visiting this one, it is equivalent to this minus this, okay? So, we take it 35.844 minus 10x, and then, since we minus it, okay, so this minus this loading, so since supposed to be it has a negative shear, okay, its effect on shear will be negative because it's downward, but since it is a negative area, in order that its equivalent will be like this, so it will become positive, okay, so positive, okay, just remember, okay, so it is equivalent to this loading minus this loading, so it will become positive, okay, positive, okay, so remember the formula here, this, okay, negative wx minus a squared over 2l, okay, and the a here is 4 meters, okay, a is 4 meters, okay, its distance from the leftmost support, and its l, or the length, is 3.5 meters, okay, so we have 10, okay, so we have 10 times x. The a here is the distance of the leftmost support to the beginning of your rectangular loading. So minus 10 plus 10 times x minus 4, and the squared, okay, over 2l. The L here is 3.5. So 2 times 3.5 will be 7. So it will be 7. So this will be your shear formula. Shear equation at section 3. And then we have finally the moment. So we have moment is equivalent to, okay, 35.844 x minus, okay, so the other way around, in order that you will not get difficulties, is just to integrate your shear, okay, so it will become minus 5x squared, okay, plus 10 over 21 times x minus 4 to the power of 3. So this will be your moment, okay? This will be your moment equation, okay? Similar to this, okay? So if you use this table, okay, it's over 6 times L. 6 times 3.5, which is the L, it will become 21, okay? So what we do here is exact, okay? So now, we're going to write, to draw your shear and moment diagram, okay? But first, we will erase everything yet, okay? So we will transfer, okay? Okay, so do not worry, since this is a video, you can repeat those moments so that you can understand, or you will understand in what steps, why we come up with the incoming solutions, okay, in the few moments from now. So we have, okay, so let's copy, okay, for section 1 should be V is equal to 35.844 minus 10x. Okay, so I will going to copy each and every shear and moment equation, okay, so that we can draw the shear and moment diagrams in this area, okay, so because we have limited space. Okay, so I will slowly erase. Then the M is 35.844 minus 5x squared minus 8. And then section 3 is okay. Then moment is okay, I'm sorry. So in this moment, we'll also add this negative 8. Okay, so since there is an effect, so this will be 10 minus x minus 4 minus 8. Okay. Minus 8. Okay, so this will be a part of your equation na 8, negative 8. Okay. Okay, so these are the, okay, x equals to 3 to x equals to 4. X equals to 4 to x equals 7.5. Okay. So we can now draw your shear and moment diagram. And then we can check whether this our computed reactions are correct. Okay. this is your Vx diagram, and this is your moment diagram. Shear and moment diagrams. Okay, so this will be your zero line. Okay, so this is the line in which the values will be zero. Okay. Okay, so first we'll go to section 1. Okay, so when x is equal to 0, obviously, okay, you substitute in this shear equation. When v is equal to when x equals to 0, our value will become 35.844 kilonewton. Okay, so let us put it here. And then it will change. Okay, so since this is negative 10x, so this is a distributed load, so its behavior in shear direction will be slant. Okay, will be like this. Okay, okay, but somehow we do not know in what value it will intersect this line, on the line in which v is equal to 0. Okay, so let us equate this first to 0. So what will be the value of x that shear will be momentarily will become 0. Okay, so we equate this one to 0 in order to know. Okay, so we have 35.844 minus 10 alpha x equals 0. Okay, so we have 3.5844. Okay, so somewhere here, it will intersect the 0 line. Okay. So it should be, okay, so since this is a 0 degree curve, this will be a 1 degree curve or a slant height. Okay. So if you did not, if you don't understand it yet, please watch part 1 of our video series. So this will be, okay, it will intersect at x is 3.5844. This will be 0. Okay, so since they have the same equation in section 2, okay, so we draw a section 2 because there is a change in loading. There will be a moment. Okay, okay, so we proceed to section 3. Okay, okay, now since we know, okay, at x is equal to 3, obviously it will be 35.844 minus 10 times 3. Okay, so that we all okay, so this point will be 5.844, and then at the end, at x equals to 4, we substitute. Okay, so 35.844 minus 10 times 4 is negative 4.156. So it will be negative 4.156 kilonewton here. Okay, and then we have this loading, which is triangular. Okay, so since this is triangular and this is a 1 degree curve, okay, this is 0 degree curve and this is 1 degree curve, so this will be a 2nd degree curve here. It will act like this. Okay, it will behave like this. I mean, it will behave like this. Okay, so since it is a larger triangle, so it will be flat. Okay, it's not like this. I'm sorry, it would be like this. It would be flat. it's the reverse. Oh, if it is triangular like this, its behavior will be like this. But if it is like this, it will be flattened. It will be like this. It will go down like that, okay? This type of loading. So if this is 1 degrees, this will be 2 degree curve. Okay? So this is already discussed in part 1. So we will find its value at the end. Okay? So what if your x is equal to 7.5? So let's compute 35.844 minus 10 times 7.5 plus 10 divided 7 times 7.5 minus 4, 3.5 to the power of 2. So we have, okay, it should be like this, okay, flattened. So it will have negative 21.656 kilonewton. And since we have an upward force of 21.656 kilonewton, we add it to here. So at the end, it will end up at 0. Okay. So this will be your shear diagram. Okay, so this is a 2 degree curve. And then what about your moment diagram? Okay. So for your moment diagram, it will obviously become 3 degree here. Okay. And this will become 3 degree. Okay. So increasing from your load diagram, it will increase 1 degree. And then from your shear diagram, it will increase 1 more degree to become moment. Okay. So that is how you draw your lines and curves inside your shear and moment diagram. Okay. So we have, okay, we'll concentrate at the moment. Okay. So we have m is equal to 35.844 minus 5x squared. Okay. So when x is equal to 0, obviously your moment will become, okay. So I'm sorry, it should be x. There should be x in this area. Okay. It's a fraud. Okay. I'm sorry. Okay, so when x is equal to 0, obviously, you will get 0. Okay, I'm sorry. So, please be extra careful when solving, okay? Because you might not get necessarily the correct answer, okay? So, since this is a negative, okay, it is spacing at this moment, so we will have a flattened curve. Flattened, since this is a 1 degree curve, it will be a flattened 2 degree curve, okay? So it starts at 0, and then when x is equal to 3, you will have (62.532), okay? It will do like this. It should have x here, okay? So in order that you will not find, okay, you have a clue if you are doing it wrong or right, just remember that your moment is just the integrand of your shear, okay? Your moment is always integrand of your shear. But somehow, there are only times in which your moment has a constant, okay? Just like this, okay? Okay, 35.844 in shear diagram, it will become 35.844x in moment diagram, and so on. So here, okay, so we have already computed the end values of section 1. What about the end values of your section 2? At x equals to 3, okay, 35.844 times 3 minus 5 times 3 squared minus 8. So 54.352. Okay, so there will be a sudden drop. It will become 54.352 here. Okay, it will be a sudden drop here, linearly downward. And then um, there is a value in which there is an increase. Okay, so there will be, okay, so here it will be 54.352 kilonewton meter, and then there will be a sudden, okay, so there is a point where of shear, zero shear, so there will be a sudden increase, or there will be a momentarily increase at that point, and then it will go down again. Since this it will start a negative area. Okay, so since x is equal to 33.5844, so okay, so we compute the value of your moment at x is equal to 3.5844, where your v is 0. Okay, and then we substitute it here. So 35.844 times 3.5844 minus 5 times 3.5844 squared minus 8. So 56, okay? So there is a value here which is equivalent to 56.240 kilonewton meter. Okay? So in this area, okay? Okay, so how to elaborate this? Okay, so this portion we will have 54.532. Okay, so we will put it here, 56.240 at this point, and then we have at x is equal to 4. Okay, at the end, what if x equals to 4? 5.844 times 4 minus 5 times 4 squared minus 8. So 55.376 here. At this point, okay? So it suddenly rise up and then go down. And then we have negative 21.656. Okay, so we will check if this will equate to 0 at x equals to 7.5. Okay? So since we are done when x is equal to 4, okay? So let us try. So if it will not equate to 0, then there is something wrong with our solution. Okay, so 35.844 times 7.5 minus 5 times 7.5 squared, I know, okay, correct, plus 10 divided 21, okay, 7.5 minus 4 is 3.5 to the power of 3 and minus 8. Okay, so negative 3.333 times 10 to the negative 3. So very small value, almost 0. So it will become 0. Okay, so you might be saying that, sir, it will not end at 0. But since it is a common sense that we have some round of error, so if you will get if a very small value close to 0, for example, negative 0.000001, so your solution is correct. It's just you have get you have just got a round of errors. Okay, so this will be a 3-degree curve here. Okay, so since we end up at 0, so therefore our shear and moment equations are correct. Okay, so this is our example number 5 for shear and moment diagrams, part 7. Okay, so we will have another example on the next video.